All right, this is the first of two videos I'm going to be posting today about energy. This one will be about just using conservation of mechanical energy, and the other one that'll be posted a little bit later is going to be about the work energy theorem and what you do when you have non-conservative forces. So for today, for this problem, we have a 5 kilogram block that's released from rest at a height of 0.64 meters above an initially uncompressed spring with a spring constant of 720 newtons per meter. And we want to know with what speed the block strikes the spring and what the maximum compression of the spring will be. So a good first thing to do here is to draw ourselves a picture. We have our 5 kilogram block that is some height above an initially uncompressed spring with a spring constant of 720 newtons per meter. And this height right here, the distance we are above the uncompressed spring, that is our 0.64 meters. So that should be enough of a drawing to at least get us started here. And we can go to part A. So part A, we could do with our other approaches that we've learned so far. Namely, this is just a freefall problem in part A. So we could use our kinematic equations with acceleration is 9.8 meters per second squared down and solve this problem easily. But for today, I'm actually going to use total mechanical energy conservation because it will work just as well, maybe even a little easier, and it will allow us to get some practice with this solution method. So total mechanical energy initial equals total mechanical energy final, or the total mechanical energy is conserved. So first of all, we have to make sure that we can actually use total mechanical energy conservation. To use this equation right here, we need a couple things to be true. All forces that we have in the problem must be either non-conservative, all forces must be conservative forces, namely the weight force and the spring force are the two most common conservative forces, or those forces must do no work. For example, the normal force is one that's non-conservative but does no work because the angle between the force and the direction of travel is always 90 degrees. So to check here, our only force is weight, which is conservative, so that one's fine. And it's the only force we have, so we are good to use total mechanical energy conservation. Now what we want to do here is we want to define our initial and final points first. Well, I'm going to label a few points in this problem. I'm going to have A be when we release the block from rest, B be when the block strikes the spring, and C be when the spring reaches its full compression. So here, I'm going to take my initial point as point A, because that's the very beginning of the problem, and I want to learn something about point B. I want to learn the velocity this block has at point B, so that needs to be one of my points. I'm going to make that my final, because the one between initial and final that you don't know anything about, that you're trying to solve for your unknown from, that needs to be one of your initial and final points. So you should make the other one a point you already know something about. We know a lot about what the block is doing up here at the top. So with that, now we have to look for what kinds of mechanical energy do we have present at each point. In order to do this, there's one thing that if you've been following along at home, you should say, Dr. Mikula, you forgot to define H equals 0. For gravitational potential energy, you have to pick which point you're going to call 0 in terms of the height. I usually pick the lowest point in the problem to avoid negative numbers. That'll turn out to be a little different today because my lowest point is at part C. But I have no idea how far the spring is going to compress yet, so it would be awfully hard to find numbers. So I'm just going to make point B my H equals 0. So for total mechanical energy initial, we go through our options. And our options for total mechanical energy are kinetic energy, gravitational potential energy, and spring potential energy. And you have a few questions you can ask yourself for each one of these to figure out if that energy is present. For kinetic energy, you want to ask yourself, is it moving? Anything that is moving will have kinetic energy. For gravitational potential energy, you want to ask yourself, are you at h equals 0? If your object is at the height that you've called 0, you will not have gravitational potential energy. And if you're at any height other than 0, you will have gravitational potential energy. For the spring potential energy, you're going to ask yourself, is the spring compressed or extended? Or compressed or stretched? If the spring has been compressed or stretched, then you will have spring potential energy. So, to begin with, at point A, the block is released from rest, so we have no kinetic energy to begin with. We are not at h equals 0, so we do have gravitational potential energy at point A. And we do have a spring, but the spring at point A, when the block is up there, is not stretched or compressed, so that means we do not have spring potential energy to begin with. And then the other side of the equation, kinetic energy, at point B, the block will definitely be moving, so we do have kinetic energy. We are at h equals 0, and when h equals 0, gravitational potential energy equals 0. So no gravitational potential energy at point B, and we've just made contact with the spring, so the spring hasn't had any time to squish or stretch yet, so we do not have spring potential energy. Once we get to this point, now we can bust out our equations. So gravitational potential energy is mgh, and I'm going to label this h with a subscript a for the height at point A, equals 1/2 mv squared for kinetic energy, and we want the speed at point B. So that gets this problem set up. Sorry, that yellow is probably not a very good color, so I'm going to switch back to my blue here. And we can start to plug in some numbers. Well, our mass will cancel out, so our answer to part A does not depend on the mass. So we'd get the same answer with 5 kilograms, 10 kilograms, 1,000 kilograms. And start to plug in for the rest of our values. 9.8 meters per second squared is g. No negative sign. G is just positive 9.8. H is 0.64 meters. And that equals 1/2 times VB squared. Now you can do a little math here. You multiply 9.8 and 0.64. You multiply both sides by 2. Then you take the square root, and you end up getting the speed at point B is 3.54 meters per second. This is the speed, not the velocity, because kinetic energy is a scalar. It doesn't care, it does not have a direction, so there's no way you can get a direction out of this equation. We know, just from common sense and the direction of the acceleration, that the block will be traveling downward. But that's the speed we need. Here, we cannot use the work energy theorem, or actually for part A, we could use the work energy theorem and we could use F equals ma. Part B, on the other hand, we will not be so lucky. Again, in part B, we can start with total mechanical energy initial equals total mechanical energy final, i.e. total mechanical energy is conserved. But our condition that we need to satisfy to use this equation is still there. So now we need to double check all forces we have in part B. Well, we could still have the weight, which is still a conservative force. And now we might have, or we will have, the spring force as well. And the spring force is equal to K, the spring constant, times X, the compression of the spring, with a negative sign to tell you whichever way you squish or stretch the spring's going to pull or push in the opposite direction. So all of these forces are conservative, so we're good to go using this equation. And next we'll need to pick initial and final points. It's worth noting that the spring force is not going to be constant through this problem. So when the forces aren't constant, the acceleration's not constant, and we cannot use F equals ma and our kinematic equations. Well, not without calculus anyway. For the same reason that the spring force is not constant, we could also not use the work energy theorem, again because the spring force isn't constant. The only way to handle that would be with calculus. So jumping back into blue here, because why not? Now we look at our initial and final points and figure out what forms of energy we have present. We know we want our final point to be at C because we want to know how far the spring compresses. And the spring's at its maximum compression at point C, so point C better be involved somehow. For our initial point, we could actually use either A or B. I'm going to use A. At point A, we have, again, just gravitational potential energy. And at our final point, we ask ourselves all of our normal questions. Is the block moving? Well, at the spring's maximum compression, no, the block is not moving. If the block were still moving, then that would mean the spring is still compressing, so we aren't to the maximum compression yet. So no kinetic energy. Gravitational potential energy. Point C is not at h equals 0. So we actually do have gravitational potential energy at point C. And because we are lower than h equals 0, we're going to have a negative height. So we'll get to that in a minute, though. And then lastly, spring potential energy. Well, we ask for the maximum compression of the spring, so presumably the spring is compressed, and we do have spring potential energy at point C. Now we can bust out some equations, start plugging in. mgh at point A equals mgh at point C plus 1/2 k x at point C squared. And here our mass does not cancel out because this last term, the spring potential energy, does not have a mass in it. So there's nothing much we can do about canceling anything out. We just have to start plugging in. So let's start plugging in values we know. We know the mass is 5 kilograms. G is 9.8 meters per second squared. HA is 0.64 meters. This is the same as the left side of the equation from part A. And now, on the right-hand side, we still know the mass. G is still just 9.8 meters per second squared. But we don't know the final height yet, so I'm just going to call it HC for now. And keep going with our equation. 1/2 K is 720 newtons per meter. And we do not know the final spring compression, XC, so we just leave it as XC. And now we run into a little bit of an issue. We have two unknowns in this equation. So that's not good. So to solve this equation, we need there to be only one unknown. So a simple fix for this, or something you can go looking for, is to ask yourself the question, grammar. Are HC and XC related? Well, over here on the diagram on the left, XC is going to be however far the spring compresses until the block reaches a speed of 0 and the spring reaches its maximum compression. So at this point down here at C, our height is whatever the spring compression is, we are that far below 0. So our height at point C is just whatever the spring compression is with a negative in front of it. So, since we can relate our two unknowns to each other, we can still solve using just this one equation. So working through the math a little bit, we have 31.4 joules on the left side over here equals, let's see, we have 5 times 9.8 is 49 newtons. The height is negative xc. And then this last term is going to be 360 newtons per meter times xc squared. So we have an x squared, and we have a number with no x's. This is a quadratic formula. To do a quadratic formula, you need to move everything over to one side of the equation. So 0 equals, with a little bit of rearranging and dropping of units, 360 x squared minus 49x minus 31.4. And as far as your quadratic formula is concerned, this 360 is your A. The negative 49, you have to include that negative sign, is your B. And again, the negative 31.4 is your C. I've already got another video on the quadratic formula, so if you need a little extra help, go watch that video. And I'm not going to show the full thing here, but you end up getting that x final, or we've been calling x at point C, the spring compression when the block is at point C, is 0.371 meters, or negative 0.235 meters. We don't expect our spring compression to be negative, so we can cross that one off, and there's our answer. The spring is going to compress by 0.371 meters. Just as a note, you could very easily use B as your initial point here. The equation would look relatively similar, except on the left side at point B, we have kinetic energy, where the velocity would be what we found in part A, would again equal gravitational potential energy at point C plus spring potential energy at point C. And again, H at point C would still be negative xc. So you could work through that again and you should get the same answer. That's it for this problem. I will be posting another one relatively soon, but these will be helpful for the homework that's due on Friday, as well as for the types of energy problems that I like to put on my test. Thanks for watching. Have a good day.